call is now being recorded.
Okay. So for the first part of the lecture, let's look at the numerical example of the k-means clustering and also EM clustering, okay? So that we understand like the gist of, all different formulas that we were looking at last time. Okay, so let us consider the following data points. Okay, and let's say, so I'm trying to draw clearly, okay, so that we can take a look together. I'm not very good at drawing that much. Okay, so in this case, let's consider the 2D case. It means that each data point has two entries. Okay, so let me write down the first axis as Z1 and the second axis as Z2. The reason I don't use X is because when we use X, they will start to get confusing, okay? Because each data point is gonna be X anyway, okay? So here, let us consider data point is 2D, and so we have data points x1, x2, all the way to x8, okay? Which means there are 8 data points, and each one is 2D, okay? So it means that I have x11 and x12, okay? So let's take a look. For simplicity, I'm gonna write down the data points in the integer numbers so that it's a bit easier to compute later on. So let's say that the first dimension is 1, 2, 3, 4, and then I have 5, 6. Then for the second dimension, I have 1, 2, 3, 4. Okay. And then what are the data points here? So the data points are as follows. Let me use the red color so that it's a bit easy to see. Let's say that we have data points here, 1, 1, 2, 1, okay, 1, 2, 2, 2, and then 3, 2. And additionally, we have some more data points at 2, 3, and 3, 3, and also at 2, 4. Okay. Because we have 8 data points and we have to do clustering. So let me write down each one so that we understand what it is. Say this is x1. Oh, the color is not so clear. I use, okay, let me use this color. So this is x1, x2. I just write down the number, okay? 1, 2, 3, 4, 5, and then 6, 7, 8, okay? So these are the data points that we have to do clustering. So what I'm going to do is I'm going to show some steps in the k-means clustering and also the EM clustering so that we understand, okay? So first, let's start from the k-means clustering. Okay, Well, one of the things we need to know is how many clusters are there. So here, let us consider number of cluster that will be used for both k-means and also the EMM as 2. Okay. So there are 2 clusters, and so let's call first cluster as C1 and second cluster as C2. Okay. So for the step number 1 in k-means clustering, first you have to set up number of cluster. No, I think last time we set number of cluster as k, right? So I'm gonna write down k is equal to 2, and we have cluster 1, cluster 2. Okay. Actually, here I used a very strange fonts. Okay, so this is a C with a very big head. Okay, and then in the step number 1, we also have to initialize the centroids. Okay, so let us randomly choose the centroids to be C1. Let's say it is equal to, let me call it to 1. Okay, just for simplicity, so that when we compute it's a bit easy. And then C2, for C2, let me set at 3, 2. Okay. So you notice that I, just for simplicity, so I set the centroid, the first centroid at 2, 1, which is around here. This is first centroid. And the second centroid, I set it here. Okay. So these are, well, I mean, you can change numbers, no, to be random, so that you can try it out. And okay, so let's take a look. So how does it work in k-means clustering? What we need to do is, for step number 1, we define the number of clusters. We randomly choose the centroids. I mean, you can choose any centroids you want. Here, because we have 2 clusters, so we set up 2 centroids. Okay, that's the numbers. What is the second step? So the second step is we have to compute, okay, the Euclidean distance. Euclidean distance between each data point, which is xi, and C1 and C2, which is centroid 1 and centroid 2. Okay. And then step 3, wait, I think it's step 3, right? Okay. Actually, it's in step 2 still. 2a is to compute the Euclidean distance between each data point. You can call data vectors, okay, as well. Because when you do programming, you have to assign vectors, either in MATLAB or in Python. And in 2b is to assign, and then once you compute the distance, you have to assign each data point to either C1, oh, sorry, not the, no underline, because we're talking about now cluster, either cluster C1 or cluster C2, okay. Well, basically we assign X1 to the cluster that is, that has a smaller smaller distance, okay, to the corresponding centroids, okay, corresponding to smaller Euclidean distance. So Euclidean distance, you can say D, okay. So you compute the I1 and the I2. Smaller of the I1 and the I2, okay. This thing has no dot, let me erase it. Oops. Okay. Okay. So that's okay. So next, let's do step number 2. So what we do is for step number 2, we will compute all the Euclidean distance. Okay. So let's take a look. Oops. Okay. Oh, sorry. Why am I at the last page? Oops. Okay. Were you able to write okay on previous page? Oops. What did I do? Ah, I see. I can move it, right? Why did I start at the last page? That's strange. Okay. So this is the earlier page. Okay. So for step 2A and 2B, that's what I'm going to do, right? So we will divide each page into 2 parts. So on the left-hand side, it's going to be computation related to centroid 1. So centroid 1 is 2, 1. Okay. And then centroid 2, this one is 3, 2. Okay. And I have 8 numbers. I'm not going to compute in detail 8 of them because I have already computed some of them. So that we can take a look together. Okay. So let me divide it. I don't know, maybe 1 page is enough. Okay. So let's see. I don't know if you all can. Maybe I should ask you to try to compute as well. But let me start from the first one. Okay. So the first one I compute the Euclidean distance between data point 1, data vector number 1, and then with the centroid 1. Okay. So this is gonna be equal to I can write it as this. What is D1? If you take a look on the previous page, D1 is 1, 1. And then with 2, 1. Okay. And in order to compute the Euclidean distance, so what you do is like this. Square root of the number on the first axis, subtract from each other, and then square, and then plus the number at the second axis, okay, subtract from each other, and then square, okay. So what you have is what? This is 1 minus 2, which is minus 1, right? And then square, so you get just 1, okay. Okay, so this is called I can call this as D11, okay. And similarly, if I compute it, the Euclidean distance between x1 and c2, okay, it's going to be the distance between the vector 1, 1 and 3, 2. Okay. Let me show you and I let you do the rest. What, maybe one for each, okay? So this will be square root of 1 minus 3 squared. The subtraction, the difference between value at the first axis, and then add it together with the difference between second axis, which is 1 and 2 squared. And what do I get here? Square root of 4 plus 1, okay? So I get the square root 5, okay? So let me ask you all to do one each, okay? Who wants to do, let me call this as D1, 2. Okay. So who wants to do D2, 1, the distance between X2 and C1, okay? You will do both, no? So that we can compare, right? I'll let you do it. Okay. Can Pio work on D21 and D22? how about
Yes, Ajahn.
you can, right? I don't see everyone's here. I don't know who else is here. Let me see who else is in here. Okay, I can see. Kittipan, can you do D31 and D32? And how about D41 and D42? How about Pimason? Let me call each one by order.
Yes, Ajahn.
Okay, Tanatson, can you help me do D51 and D52?
Yes.
Okay, and the next one is Tananpat. Can you do D61 and D62 for me? And Fanat, oh, actually, very nice. Fanat, can you do D71 and D72?
Okay.
Okay, and then Tiravit, can you do D81 and D82? Okay,
Okay.
so it's less work for me. Actually, I've done them all already, but I just want you to do as well. Okay, so I give you like a few minutes. Okay, if you want to know what are the values for each data point, you can refer to this page. Yes, okay. They are integers just for simplicity. So whoever finish whichever one assigned, please just say it, okay?
Ajahn, can I see the value again?
See what?
Can I see the values again? I want to go find.
It's here. Yeah. Let me write down the value for each one, okay, on the up here, so that just in case. So x1 is 1, 1. Okay. x2 is 2, 1. And then x3 is 1, 2. Let me erase some of these. Okay. Okay. X4 is 2, 2, right? X5 is 3, 2. X6 is 2, 3. X7 is 3, 3. Okay. And then X8 is 2, 4. Okay. Okay. So here, instead of if you don't do 2 clusters, you do 3 clusters. You just follow the same approach. Okay. We just have 3 centroids, and then when we compute the Euclidean distance, we have to compute the Euclidean distance between the data points and 3 centroids. Okay. However, in this example, we only have 2 centroids. Okay. I lost another page. Okay. Okay, so what do I get as D21 and D22? Anyone? How about D31 and D32? What do you get, Pimason?
I got both 1.
For D31 and then D32?
No, for 1.
Or 4, 1. Yeah, that's right. It's 1 and 1. Okay, thank you.
0s and square root 2 as in 42 ones and 2
Okay, 0 and square
square
root
root
2. Okay, so, okay. How about D5, 1?
Square root 2 and 0.
Okay, thank you. How about, okay, Kitipan, if you finish with D31 and D32, just say anytime, okay? How about D6, 1?
True and 1, teacher.
D6, 1?
2,
And
1.
are you sure? Are you sure? Maybe either I'm wrong or you're wrong.
Square root 2.
Yeah, I think square root 2, right? But when I did it, I used programming to do it, so it's quick. Okay, how about D7, 1?
Square root 5 and 1.
Square root 5 and 1. Okay. And how about D8, 1 and D8, 2?
3 and square root 5.
Okay, good. Wow, and I'm sure you compute it with your hands, no? Right? D31, Kitipan, you get D31 yet? I hope that you all have computed Euclidean distance before. If it's the first time, maybe you get confused. Okay, instead of waiting, let me just write it out, okay? Okay, so this is the second step. Well, thanks anyway for trying. This is second step. So we compute the distance between each data points and the centroid ones, okay? So the left column is centroid ones, okay? This is centroid 2. As mentioned, the centroid at the beginning, we don't know what should be the good centroid, but here I just put it up, just for example. Okay, so next, step number 3 or step number 2b, what we will do is we will assign each data point to the central, to the cluster with the smallest Euclidean distance. Okay, so okay, for the first one, x1, what should I assign? Let me write on this sign of cluster 1 and then cluster 2. Okay, so for cluster 1, okay, x1, should x1 be in cluster 1 or cluster 2? Okay, I did D11. Oh, let me do from D11. No, let me do first, no, and then your turn. So D11, you know that the distance between data point 1 and the centroid 1 is 1. The distance between x1 and centroid 2 is square root 5. Therefore, x1 is closer to centroid 1. So we will write x1 here under cluster 1. Okay. How about D2? Should D2 be in cluster 1 or cluster 2? Can anyone answer? Or you can read into your data points that you worked earlier. Okay. So data 2, as you see that the data point 2 is closer to cluster 1 than cluster 2. So I write x2 here. Okay. How about data point 3? Who computed data point 3 earlier? Is it Pio? Hello? Is the, oh, okay, it's still connected, right? Okay. How about data point 3? Should it be in cluster 1 or cluster 2?
Cluster 1.
Cluster 1, because the distance between data point 3 and centroid 1 is closer to centroid 1 than centroid 2, right? Okay. So x3. How about x4? x4, We don't know, right? And because it's equal, but let me write centroid 1 anyway. Just it depends on our condition. Because when you say it has to be closer to the other one, sometimes we say less than or equal, doesn't matter. And then if you follow the same approach, you notice that starting from D5, starting from x5, x6, x7, x8, they are closer to the centroid number 2 than centroid number 1. So I write x5, x6, x7, and then x8. Okay. And the good thing about doing this, the Euclidean distance is if your data is not just two-dimensional, if it's one-dimensional, you can find the distance as well. If you have the data points and the centroids, which are three-dimensional, four-dimensional, and so on, you can still use the same approach. Okay, so I mean, it's very, in a way, it's quite generic. Okay, and this is 2B, right? 2B. So here we assign 4 data points to centroid 1 and then 4 data points to centroid 2. So when we go back to the previous page, so if you take a look, okay. So what we do here is, so we have 4 data points, okay, in cluster 1. Okay, so let me call this as cluster 1. And then let me use the green colors. So for this, it is C2, okay? And you can sort of notice that, when they start to do the clustering, there seems to be some sort of circle around data points in a way, okay? And this is very unique for k-means clustering. Okay, next, let's do the next step. The next step is, this is the first iteration. So once you assign the data points to each cluster, next you have to recompute the centroids. Okay. So we will, for step number 3, oops, I lost page again. Step number 3, okay, so we will recompute the centroids C1. Let's call this a step iteration 2, and then centroid 2 iterations 2. Okay. So, well, how do we compute it? We compute the centroid 1 at the next iteration as the average between all data points within that cluster. Okay. So here, because there are 4 clusters that we assign, so we have x1 plus x2 plus x3 and then plus x4. Okay. And if you compute it out, you get something like 1.5 and 1.5, but actually, let me show you just for fun, okay? And what is x1? x1 is 1, 1, 2, 1, 1, 2. And 1, 2, and then plus the x4. What is x4? x4 is 2, 2. Okay. This will be the new centroid, okay? So you can just sum them up, 1 plus 2, you get 3, becomes 6, 6 over 4, you get 1.5. And at the bottom, you also get 1 plus 1 plus 2 plus 2, over 4, you get 1.5 and 1.5, okay? Notice that when I write down on earlier pages, I write them like this. If I write this the same way, it's going to be like this, okay? But both ways are equivalent in this case. Okay? Actually, to make it more easy, to make it easier for programming, actually I should write it as in the vector terms instead of like the column vector term. Okay. so people understand it better. So now you see that for C1, 2, this is what we get. And then similarly, if you compute the centroid 2 at the second iteration, you get, if you do this, you get 1/4 because there are 4 data points, 1/4 plus x5 plus x6 plus x7 plus x8, okay? And if I compute it, what do I get? Can anyone say x5? So I don't have to go to previous page. What is x5?
3, 2.
3, 2. Okay, how about x6?
6, 2, 3.
2, 3. How about x7? I think it's 3, 3, right? I remember, right? And then x8, I think x8 is 2, 4. Thank you. Okay, so we just sum it up like that. So here you see that you get 3 plus 2, you get 5, plus 5 plus 5, you get 10, 10 over 4, you get 2.5, right? And then at the bottom, you get 2 plus 5, which is 5, 2 plus 3, you get 5, 5 plus 7, you get 12, 12 over 4, you get 3. Okay. So during next iteration, what's going to happen is, if you go back to the previous page, C1, 2 is now moved to 1.5, 1.5. Okay, so now let me use the green color. Okay, so now the centroid is moved here to the center. Okay, so this is C1, 2. So it's moved, no? And then for C2, C2 is moved to 2.5 and then 3, which is here. Okay, so the centroid is moved. So what else do you do? Well, I mean, for this is step number 3, right? Step number 4, so we repeat step 2 and step 3. Okay. So step number 4, so we repeat step 2 and 3 until what? Until both centroids C1 and C2 do not change. Okay, well, do not change mean they're like they converge. You can say they converge. Okay, or the number of maximum iteration, okay, is met. Okay, let's say you want to do this process for 10 iterations. So it maybe either the centroid, you know, they converge or they change slowly, you stop, or because you have number of iteration, then you reach actually not met, it's reached. Okay, if you reach the maximum number of iteration, then you stop. Okay, so that's how you do it. Okay, so actually K-mean is not that difficult. You just keep doing it and so on. When I write the programming for this example, it doesn't take long. Actually, just 2 iterations, then it stops. Okay, and then that's how you write as answers. Because the K-mean clustering and also the EM clustering, they're supposed to be unsupervised. Okay, so it means that we don't even know what cluster they should belong to, but we use some criteria to assign the clusters to them. Okay, and then of course you work with different objective, or you work with some prior known knowledge and then see whether you can sort of like trigger, and then see whether the cluster, is what you sort of expected. Okay. And sometimes k-means clustering, they use another name called k nearest neighbor. Maybe sometimes you'll hear something like that. Okay. So that's another name for this method. Okay. Okay. Next, let's do the same example, but now we will do it for EM algorithm. And actually, it's more involved. So anyway, I probably will not ask you to help me compute it, but let's take a look at it. Okay. Last time, I remember when I talked about the EM clustering or EM algorithm is quite long, right? But then I think with the example, it's going to be much clearer. Okay, so next, let's take a look at the, for k-means clustering, do you have any questions before I go to the EM clustering? The reason why I want to look at the details examples, because there are a bunch of parameters, that they float around, and when you only see these variables or these parameters in equation, sometimes it can get confusing, right? Okay. So for EM clustering, it's actually very similar. You have, let me see, how many steps do you have? Okay, you still have 3 steps or 4 steps as before. So steps number 1, we set the number of cluster as 2. Okay, you can set more if you want. And similar to the previously, we call cluster 1. So this is CB, the big heads, okay? And cluster 2. And also for EM clustering, they also give the weight between each cluster, okay? So let me start by saying that alpha, which is the weight, to be 0.5. Okay. This is like the weight of, actually this is the weight of cluster number 2. Okay. From last lecture, when we were looking at this, we sort of we compute based on cluster 2. Okay, but today I will show like how to compute. How do you get at each step? Okay, and then for step number 1, which is initialization, we have to set up the mean and the variance. So for cluster number 1, the mean is set up. I put underline here to show that it is like vectors. Okay. So let me actually write in terms of vector from now on so that we don't get confused. Okay. And then for cluster number 1, we also have the sigma. Sigma, let me put it in here as 1, 1. Okay. And for cluster number 2, let me put the mean similar to the previous example that we saw earlier. So let me put down 3, 2. And for sigma, because at this point we don't know what should be the sigma, okay, then we put 1, 1. Okay. So this is similar to the centroids that you saw earlier. In fact, it is similar to C1, and this is similar to C2, as in the previous example. Okay. However, for EM clustering, what it does is in each dimension, okay, so you have like, if you have one dimension, you have like Gaussian, like that, okay? Then you have like the mean, okay, and then you have the variance, okay, mean and variance, and standard deviation. So if this is 1D, okay, but then when we talk about 2D, it's going to be like this, because here we have a 2-dimension. So here we have something like this. Okay, so the center here, this is where mu is, which is the mean vector. Okay, because there are 2 dimensions. So if you look from dimension 1, which is the blue line, you have to assign sigma as well. If you look at the Gaussian for the 2nd dimension, you will have sigma as another number. So it means that it doesn't have to be like a circle, or they don't have to be symmetric. Okay. So sigma 1 doesn't have to be the same as sigma 2 because no need to be symmetric. To be symmetric. Okay. So if you have one sigma is small, one sigma is large, it means one dimension has very, if you have one dimension, let's say the blue line has very small standard deviation like this, then that Gaussian is very small. Okay. And then if sigma 2 is much larger, then it means that the second dimension, this Gaussian is huge. So they don't have to be the same. Okay, so that's the first step. And then, okay, let's go to the second step. So the k-means and EM are very similar in this way, right? I think the important part is also in the second step, which is the XE step. Okay, so in the k-means clustering for the second step, what we do is we compute the Euclidean distance. Okay, but for the EM clustering, what we do is so there are two parts. Actually, just one part or two parts. Let me see. So there are two parts. The first part is instead of computing distance, we compute what is called likelihood. Okay, which is L of each data point and then cluster 1, and also likelihood that x1 is in cluster 2. So when we say likelihood, we means how likely is x1 is in cluster 1 and how likely is it in cluster 2. Okay. Or here you can write it as likelihood of x1, and then actually not likely, I have to say given, okay, given. But if it's cluster 1, it means it's given mu1 and then sigma 1. And then L of L1 given cluster 2 with the mean mu2 and then sigma 2. Okay. We'll show you how to compute this in detail on the next line. Okay. So let's take a look here. Have you been able to finish writing? Okay. If you haven't, please tell me. Okay. So we're going to do the same thing. Okay. We'll compute like this. So on the left-hand side, I have C1, cluster 1, and C2 and cluster 2. So we will compute, instead of we compute the distance between data points to the centroids, here we will compute the likelihood that each data point is in cluster 1 or cluster 2. I'm going to show a detailed example for one of them, and then I will show. I have computed some already, used MATLAB. Okay, so let's first see, this is the likelihood of x1 given c1, okay? And how do we compute it? Here we have 2 dimensions, okay? If we only have 1 dimension, we can just write PDF with the, okay, let me put up here just in case, okay? If I talk about 1D, if I have likelihood of x1, so it's not vector, no? And given mu1 and then sigma 1, which also not vector because 1D. Here I will get 1 over square root 2 pi sigma 1 squared. So this is a PDF of Gaussian, but we replace x here minus mu1 squared divided by 2 sigma 1 squared. Okay. So this is the likelihood that we're trying to compute, but this is for 1D, not 2Ds. Okay. So what do we do when we have 2Ds? We assume that each dimension is uncorrelated or independent in this case. So what we need to do is we will compute like this. We will compute the multiplication of two PDF. Okay, one for dimension 1 and the other one is for dimension 2. Okay? Because the x1 is, what's the number of x1? X1 is 1, 1, right? So it's very easy. X1 is 1, 1. So I have the PDF of dimension 1 of 1 given, what is mu? Okay, mu1 is 2, 1. Sigma 1 is 1, 1. Okay. So I have PDF of x value of dimension, first dimension, given the mean and given the sigma. Multiply with the second PDF of the data. The second dimension is also 1, given the mean of the second dimension, which is 1, and the sigma. Okay. And then if I compute it out, then I will get 1 over square root 2 pi sigma 1 square, so it's 1, e to the negative 1 minus the mean is 2 squared divided by 2 times 1 square. Okay. Let me write down in detail now for one of them so that you understand what it is. 2 times 1 squared. Okay, and then multiplied with the second PDF, 2 pi times sigma 1 square, which is 1 squared. I can put 1 square here just so that we follow. E to the negative of value, which is x minus mean square divided by 2 times 1 squared. Okay. And then, you just use computer or whatever or calculator to compute it out. In this case, I get something like 0.0965. Okay. Similarly, I will show for x1, but I will show for likelihood that data point 1 is in cluster 2. Okay. Mu2 is 3, 2, and sigma 2 is 1, 1. Okay. So here I will get the PDF of data points. First data point is 1, given the mean, and then sigma, which is 1. Okay. First iteration, we don't know what the sigma should be for each dimension. So we just 1, 1, okay? Multiply with PDF of the data point, second dimension, which is 1, given the mean, which is 2, comma 1, okay? And then I just write it out. Similarly, square root 2 pi times 1, e to the negative 1 minus 3 squared divided by 2. I don't write sigma square now, no, because sigma square is just 1. And multiply 1 over square root 2 pi times 1, okay? 1 to the negative 1 minus 2 squared divided by 2, okay? And for this one, if I compute it out, I get something like 0.0131, okay? So for data point 1, if I compute it out, I will notice that, hey, x1 is more likely to be in the cluster 1 than cluster 2, okay? Because 0.09 is larger than 0.01, right? But then you notice that for these two numbers, likelihood is not equal probability, okay? And so let me write at the top so that I emphasize the point. So likelihood is not equal probability. Okay. It's very clear because why? If it's probability, then these two numbers, when they add up, you need to get 1, right? But x1 can either be in cluster 1 or cluster 2. If this is probability, when they add up, then it's 1, right? But in this case, it's likelihood. Likelihood is not probability. Okay? But what we will do later is, if you from last lecture, we will normalize value so that it looks more like probability in terms of gamma. Okay? And we will keep doing this, and then for some other numbers. So in this case, let me write down a little bit more. So in step number 2, once you compute the likelihood, then you need to compute what is called gamma. Okay. And so this one will be gamma 1. Okay. So next, let's compute gamma 1. Okay. So gamma 1 is more like probability. Probability that gamma 1 is a probability that x1 is in cluster 2. Okay. Well, we can compute either way. Okay. But here, let me compute these first. So gamma 1, what is gamma 1? Basically, what we do, gamma 1 is we will use this likelihood value from cluster 2, okay, and divide it by total likelihood. So this will be likelihood of x1 given c1. Oh, sorry, c has to have big head, no? So we don't get confused. And then plus likelihood that x2 is in cluster 2, okay? So you see, we have two likelihood values. One is 0.09, the other one is 0.01, right? So here we see that x1 is more likely than x2. No, cluster 1 is more likely than cluster 2. So here what we do is we compute gamma 1 as the probability by just normalizing, okay? So what do we get here? But also we set alpha, okay? We set alpha to be 0.5 at the beginning because we don't know what it is. We just set it 0.5. So this gamma, if you compute it out, you get like a 0.5 times, here we refer to cluster 2, right? So it's 0.0131 divided by 0.5 times 0.0965 plus 0.5 times 0.131. Okay. And what do we get here? If you compute it out, you get something like 0.2687. Okay. Similarly, now is the probability. Okay. So if you compute 1 minus gamma, this will be the probability that x1 is in cluster number 1. Okay, or C with the big head, C1. Okay, so it's just a 0.7313. Okay, and this is how we compute the likelihood values and also the probability values. Okay, well, anyone has any question at this point? I think it's very detailed, right? So if you have any question, please don't hesitate to ask. Okay, I try to come up with this example because I think that it's more convincing than just looking at just the equations. Okay. Okay, so we can repeat this process. We are still at step number 2. So we can repeat this process to compute the likelihood that x2 will be in cluster 1, x2 will be in cluster 2, and then do all the way until x8. Okay, I have computed some of them already, so let me write down up here. So L of x2. Okay, let me write as another example. No, so L of x2 of cluster 1 is going to be 0.1592, and for x2 in cluster 2, I get something like 0.0585. Okay, actually, should I write down more? We will have something like this, that the likelihood of x2 is more than likelihood, cluster 1 has more likelihood than cluster 2 still. No, so this actually reflect k-means clustering as well, because if you remember in k-means clustering, the first 4 values, okay, it leans more toward cluster 1 than cluster 2. Okay, for x3, if I compute it according to the PDF, I get something like this. Okay, I don't write everything now. No, I just want to write quickly. I get 0 to 15. And then for x4, if you remember from k-means clustering, we have equal distance, right? So here we have, if we compute likelihood, we get 0.0965, and both are equal. Okay. And then if you go further to x5, data point 5, likelihood that is in cluster 1 is 0.0585. And then likelihood that it is in cluster 2, it is 0.1592. Okay. So starting from x5, the value on the left-hand side seems to be smaller than the right-hand side. And if you go to x6, for example, let me do it a little bit more. The number on the left-hand side is going to be still smaller than on the right-hand side, you know, and so on. Okay. So this is how we do it. So in a way, the likelihood will mirror, or it will be similar to k-means in a way. Okay. And then if you use this likelihood value to compute the gamma value, we'll get gamma 2 to be something like 0.2687, gamma 3 to be 0.2687, gamma 4 it's going to be something like 0.5. Don't forget, gamma is now is probability. So for data points 4, we have equal probability to be in cluster 1 or cluster 2. So the probability when computed, you get something like 0.5. And also in this case, because we still let the weight, which is alpha, to be 0.5. In the next iteration, this alpha will change. So when they change, then it means that for x4, you will not get 0.5 anymore. Okay. And then gamma 6, gamma 7, gamma 8. Let me just write down what I computed earlier. Okay. And then I will get something like 0.7313. I use MATLAB to compute it. And here's 0.7313. Gamma 7, 0.8805. Gamma 8 is 0.8792. Okay. And if I write down gamma 1 as well, gamma 1 earlier was, okay, 0.2687 as well. Okay. Okay, so you see that here, actually, gamma, which are probability, you know, the probability that the data points will be in cluster 2, so it's quite small for the first 4, right? So this must be cluster 1. This must be cluster 2. Okay? I mean, when you do this, maybe you decide to let data point 4 to be in cluster 2 at the beginning. That is fine as well. As you know, as we iterate, we will have it will change. You know. So this is step 2. Okay, it's similar to computing the Euclidean distance, but it's more involved and is related to the Gaussian PDF here. Okay. Okay, now let's look at step 3. Wow, I'm gonna spend like 1 hour only on this example. Next, step 3. Step 3 is called M step. Okay, so in M step, because the algorithm is EM, right? For the M step, what are we going to compute? Also similar to k-means clustering. So for k-means clustering, we recomputed the centroids, right? For the EM algorithm, here we will recompute both the mean and the standard deviation. Okay, so let me show you. I have computed some already. So first, let's compute the mean of the second cluster, which is mu2 for the second iteration. Okay, this is gonna be a summation of gamma I xi divided by summation of gamma I. Okay. And here, we don't use data points only in cluster 2, but we use data points, use all data points, okay? We don't do it like in k-means. In k-means, you only sum the data points in that specific cluster, right? But for EM algorithm, we don't assign cluster during iteration. So we use all data points. But the probability value is gonna be like the weight, how much to consider that data points. Okay. If that data points is very unlikely to be in cluster 2, that gamma value is gonna be very small anyway. Okay. So I don't know, should I? So I mean, so here because we have 8 points, so I is equal to 1 to 8. I is equal to 1 to 8, and you can just use the gamma and multiply with the xi. Okay, maybe let me write it down just a little bit so that you get a bit used to it. No? So basically, first I is equal to 1. The first gamma 1 is 0.2687. Okay, and multiply with x1, which is 1 plus for x2, I have 0.2687 multiplied by x2, and x2 is 21. Okay. So I'm going to do this until x8, but for x8, gamma 8 is the 0.8792, and is I think it's 24, right? Okay. And then here you divide it by summation of gamma, which is 0.2687 plus 0.2687, and then plus all the way to the last gamma 8 is 792. Okay. So this is how we compute the mean, and we will get two value because it's 2-dimensional. So here we will get something like, let me write it out. So we get something like 2.2373 and then 2.6256. Okay. And if you want to find the mean for or the centroid for cluster 1, we repeat similar step, but instead of using gamma, we use the 1 minus gamma. Okay. Okay, and you just follow the process. No? So here you get something like, I have computed it out already. I get something like 0.2374 and 0.5213. Okay. So these are the mean. And you notice that, oh, sorry, I wrote down the wrong number. I get something like 0.8 1.69 and 1.76. Okay. So you see that for the mean centroid 2, the cluster 2, it moves to a different position as in the k-means. No? For cluster 1 as well, for cluster 1, I think the second iteration, the mean, the centroid is moved to 1.5 and 1.5, right? But here is moved to 1.69 and 1.76, right? Then for computing the sigma, for sigma 2, for sigma 2 square, we can compute it from summation of gamma I. Oops, I don't need parentheses here. And multiplied xi minus mu2 square and divided by summation of sigma gamma I. Okay. So you notice that this is like a equation for the variance, right? Same equation, but here we put probability at the front as well. So it's like an expectation in a way, no? And for this one, I get something like 0.2374 and 0.5213. Okay. Oops, I forgot to compute. And, oh, okay, one more. And then for sigma 1 square, okay, I do summation of 1 minus gamma I xi, but here I subtract with the mu1, not the mu2. Okay, here I will use mu2 from the second iteration and mu1 from the second iteration, so that is updated values of the mean, and then divided by summation of 1 minus gamma I, and so on, just compute it out. And 0.2126, 0.2516. Okay. So this is step number 3. Okay. And lastly, we don't finish yet. We have to recompute the alpha. Okay. For the alpha, for the second iteration, I put iteration up here. Okay. So for the second iteration, what is the alpha? For the alpha for the second iteration, using the same equation from last time, is summation of gamma I divided by n. Okay. In this case, n is 8. Okay. So I is equal 1 to 8, or n in this case. So this is 8. Right? I compute it out, I get something like 0.4028. Okay. It means that the probability, overall probability for cluster 2 is slightly smaller than overall probability of the cluster 1. Okay, so then for the next iteration, so it's step number 4. Okay, we repeat step number 2, step number 3, until the mean and the sigma j converge. Okay, or the number of iteration is reached. Okay, this is how it works for the numerical example. Okay, does anyone have any question where you don't follow? Kitipan, have you followed well? Pimason, any question?
No question อาจารย์
Okay, Pure, any question?
No อาจารย์
Thanatson, no question at all?
อาจารย์ครับลองย้อนกลับไปหน้าที่คำนวณแกมมา1หน่อยครับ
Okay. Gamma 1, let me see. Yeah, help me correct it. This is right. Okay, is this one here?
ย้อนกลับไปหน้านี้แหละครับผม
Okay.
ไอ
You get a different number maybe?
ข้างล่างครับอาจารย์ตรงที่เป็นแกมที่เป็นอัลฟาคูณกับ L ตรงตัวหารนะครับคูณกับ L แล้วก็เป็น x 1แล้วก็
Oh, yeah, exactly.
หรือเปล่า
Yeah. Yeah. One moment. Uh-huh.
แล้วก็ข้าง
Here, right? It has to be x1.
ครับ
Wait. It has to be, this is still data point 1. So it's x1.
แล้วก็พจน์ข้างหน้า
Here
เป็น
is
c1
c1. Okay.
ครับผม
That's fine? Yeah. But I use the right number, right? Yeah, sometimes the notation is a bit confusing. Okay. Good. How about Tananpat? You have any question?
For now not question อาจารย์
How about Tanat?
No.
Tiravit?
No.
No? Okay. Good. At least I asked every one of you, no? Okay. So that's the first part of the lecture. I can't believe I spent 1 hour on the example. Oh, God. Okay.